So previously we learned about Cauchy's integral theorem. So essential feature of the theorem is if you have a closed curve and you are integrating counterclockwise, and we are thinking about some region of space called domain. Enclosed by a closed curve C. And when Fz is analytic, then Fz dz is equal to 0. And also another result we obtained last class was when z naught belongs to D, this integral otherwise. So this integral is 2 pi I when n is minus 1 and 0 otherwise. And this result can be actually, instead of using two lines, we can simplify the delta m minus 1. So this, I found that many students are not familiar with this notation. It's called Kronecker delta. His name is Kronecker delta. So this says when delta m comma minus 1 means when m is equal to minus 1, then the result is 1, and otherwise 0. So this is actually a very powerful theorem, and I have shown some example about doing cosine sine integrals for 2 pi. Another example can be very simple. Let's say Fz is, say, z plus 1, z minus 3. And C is a circle with radius of 2 centered at the origin. Then I might be able to ask you a question of integrating this. Can be one of the examples. So first thing you have to do is undo the partial fraction expansion, right? So z plus 1. It's obvious. We have 2 points. One is minus 1. 3, we have a circle. I'm going to use a red one as a circle. C with the radius is 2. So actually we have only 1 point. How many points are inside of this region. So how many points can you see inside of the circle? How many? 1 or 2? 1, right? So minus z equal minus 1 is included inside of the circle. So when you do this integration, you don't need to worry about z equals 3. So only the point inside of the circle contribute this integral. So then we need to do the partial fraction expansion. C plus 1a, c minus 3b. The easiest way of obtaining a and b is when you calculate a, you just let b disappears. How do you do that? So in order to make b disappear, we can multiply z plus 1 everywhere, right? So multiply z plus 1 everywhere. You have z minus 3 over 1 equal to a plus z minus 3 over b, z plus 1. And you set z equal to minus 1. Then minus 4 is a, right? If you like to make a disappear, what do? You multiply z minus 3 everywhere. Then we have z plus 1 equal to c plus 1 over a, c minus 3 plus b. Okay, we need some barrier here. So we set z equal to 3. Then this when you set z equal to 3, then this part disappears, right? So we have only b. So b is actually 1 over 4. So a is minus 4. So let me make a copy of this. I think I have become very proficient in this business now. Set copy, delete, and new template. About so we know that a is minus 1/4, b is 1/4, so it becomes minus 1 over 4 z plus 1 plus 1 over 4 z minus 3 over b. No b, sorry. Just 1. So this actual integration only this term. So we don't need to worry about the other one because it's outside of the circle. So only this term contributes, and this is 2 pi I. So this is simply minus 4 2 pi I minus 2 pi I. There is another formula called Foucault's integral formula. Which is different from Cauchy's integral theorem. That is, when fz is is analytic on D, and Z naught is included in D. Then we have the following integral: Z minus Z naught Fc dz is 2 pi I Fc naught. The integral theorem says when Fg is analytic, then the closed integral of the closed curve of Fg dz is equal to 0. And if you divide by z minus z naught, then it becomes 2 pi I times Fc naught. So I'm going to give a simple proof. So I can move on. Proof is very simple actually. So we need to detour the so that's your original curve. And we make a slight change. As before. C prime is equal to C1, C2, C0, C3. So C prime is consisted of C1 plus C2 plus 0 plus C3. And C rho is actually in the clockwise. And in this modified contour, Z naught is outside, right? So that is your Z naught. And let's say this is epsilon, and we will do later. So the integral C prime for this prime integral, Z naught is outside, right? Outside of this whole contour. So if we do this integral, what will happen? 0, right? Because Z naught is outside. So we have 0. And this can be added as a C1 C2 C3 and let's say this is 0. Maybe I can put minus sign here because this is clockwise. And if we set epsilon is equal to 0, it becomes what? it becomes C, right? And this 2, C2 and C4, C3 are opposite direction. So if you getting close to each other, then it becomes 0, right? And we have minus zero, because 0 is clockwise. So when you do integrate, we can put minus sign. And it's actually counterclockwise. So this is 0. So I can make another point. So we have 0 is the original contour integral minus 0 actually we have to set epsilon to 0. So 0 is this. We have epsilon. So on this point, z epsilon exponential I theta, right? So z not 0, so becomes dz is epsilon exponential I theta, I d theta, z minus z naught is epsilon exponential I theta. So it becomes epsilon goes to 0, 0 to 2 pi, epsilon is I theta, f z naught plus epsilon exponential I theta, I epsilon exponential I theta d theta. But this cancels each other, and when epsilon is going to 0, this is 0, right? You can just put it out. So it becomes f z naught times 2 pi I. So that's the end of proof, QED. So course integral theorem says when fz is analytic, integral formula says when fz is analytic, then the integration of fz divided by z minus z naught on a closed contour is 2 pi I times fz naught. So it's a very simple proof, pictorial proof. So when fz is not analytic at z equals z naught, we call Z naught as a singularity or a singular point or a pole. The same meaning. Point or pole. So for example, when fz, if we expand this z minus c naught to the m, bm, if we can expand z fz as this kind of series, it's called Lorentz series. It is a name called Lorentz series. And if we have some curve z naught and z naught inside of C. Okay, so we have a very complex function which can be expanded this way. What happens if we integrate? We have infinitely many terms in this series, but when you integrate it, most of them will be zero, right? So which term will survive? This one, right? Only this term survives. I mean, no matter how complicated the complex function is, when you do integration, only this one is important. It's 2 pi I b minus 1, right? And this particular coefficient is called residue, called as residue, and written as fz naught. Written as residue. So this is also the result of course with the integral theorem and integral formula, right? So function can be very, very complicated. But when you do this integral over t, the only information we need about this function is this coefficient, t1. Function itself can be extremely complicated, but it's the only information we need. So it's a very efficient method of doing complex integration, and especially for the mathematicians or engineers or physicists in the 18th century, they didn't have a computer. So the only computing tool they have is paper, pencil, and your brain, right? So only three things they had. So they invented the mathematical techniques that can be used to calculate the very complicated complex function. And the result is you only need one bit of information, p minus 1. And it's called residue of the function, and written as this way. So how do you calculate the residue? It's very simple. But before I do that, let's make a copy of this. So again, maybe I can. So assuming Bm is the first number that is not 0, so if we multiply z minus z naught on fz and set the limit, what happens? If m is not 0, definitely m is greater than 1. 1. What happens? If we multiply z minus z naught of fz, this is m minus 1. And when you set z equal to z naught, what happens? Become infinite, right? And if we can continue this, but m minus 1 fz, what happens? Here we have z minus z naught in the denominator, and it goes to infinite, right? If you multiply fz, what happens? Z minus z naught to the m to fz, and you set z equal to z naught. You have Pm, right? Which is finite. In this case, we call the singularity, we call then z is a pole of order m because z naught is a pole of order m. But we are interested in not interested in Bm. We are interested in only B minus 1, right? But still, we are still interested in B minus 1 only. So how do we obtain B1, B minus 1 from the knowledge of this? So we found out that this singularity has order m. It's called pole of order m. But so we can do it again. But we are only interested in B minus 1. So I'm going to multiply z minus c naught to the fc. Then we have m. We have bm plus bm minus 1, z minus c naught, plus etc. Plus p minus 1, z minus c naught to the m minus 1, plus p0, z minus c0, m plus etc. So what happens if we differentiate m minus 1 times over this? The terms in front of b minus 1 will go to 0, right? And this one, if you differentiate this m minus 1 times, we'll have m minus 1 factorial b minus 1 plus b0 m minus 1, etc., z minus z0 plus higher order terms. So if you set z equal in the limit is m minus 1 factorial b minus 1. So b minus 1 is equal to residue of f z naught. It's simply this. M minus 1 factorial dzd m minus 1 z minus c naught m fc. So that's your formula to calculate the residue. And I think probably I will stop here today and continue the discussion of residue next class. And I will let you maybe 10 minutes to prepare for the quiz.